Hi, welcome back to this class. This is a Transformer Decoder class, part three. In part one, um, um, we discussed this part. In part one, we talked about output embedding and positional embedding, and then in part two, we talked about masked multi-head attention. And then in this class, we will talk about this yellow box, add, residual, and normalize. So add, residual, and normalize. And you can see just a remark here that the output embedding or positional encoding, it comes all the way out to here. And then also it goes inside the masked multi-head attention. So the output of this one, uh, sum it up with the original output that comes without going through the masked multi-head attention. So this line plus this line here that goes out. So that's our task for this video. So if we just recall or remember what we had in the part two, in part two, we got this um, uh, decoder self-attention. We got this one. And if we recall the earlier or part one, and we have Y positional encoding this part. Now we need to add this to this, okay? And that's what formula says. So residual, add residual can be found by adding Y position plus the self-attention output. So that is Y position and self-attention is this one. Now we're adding element-wise, but there's a technical problem. You can see here we have just get the black color. So this is 3 by 4, and this is 3 by 2. Okay, so 3 by 2 multiplied by 3 by 4. Um, okay, 3 by 2 multiplied by 3 by 4. Kind of different dimensions that we have. So to work out this one, we just make sure that we will make it a full dimension features. So here, two-dimension feature. So why not we will copy this again. So we will copy this one again here and copy it here. So 0.42, 0.75, 0.42, 0.75, 1.169, 1.280, 1.169, that's copy. So on and so forth. So what we did, we just copied the attention output 4 dimension to make it 3 by 4. Now, once you do 3 by 4, and this one is 3 by 4, then they can be added element-wise. So I add this to this, and I add this to this, and I sum up this with this, and I sum up this with this, and I sum up this with this, and so on and so forth. So assuming that I've done for the first token, that is how I did it. So this is the row for the first token, which is start, and for the second token is Anna, uh, done, and for the third token is done. Now, uh, then in the process, this is there are two sub-processes in this block, in the yellow block. So we have add, we did the add residual, and now we do normalization. So for normalization, we will take the token that we have. We will take the token that we have, for example, for this is the how you do normalization. each row, we do row-wise normalization. So each row will be, I mean, that's row one plus this one plus this one plus this one divided by 4. So sum of the row elements divide by 4, and then we will get the mean, and then the each element minus mean, we will get the value for it. We will get the deviations. So that's the deviation 0.374, and that's deviation 0.392, and that's the other deviation. And now we sum up this deviation and we divide it by 4, as we have 4 features in the array. We have 4 columns. So we will get the variance, and the square root of variance, we get the standard deviation. Once we get the standard deviation, we will take the deviation over standard deviation. Okay, so we will get the deviation, the difference from the sample, squared sample minus mean. We will get this value, and we will get this value for each elements in each row. So thus, for the first row, that's the result. That's for the second row, and we normalize it the second row, and then the third row, again we normalize in this way. So the final results would be this output for us. That's 3 by 4. What happens here? Each token now can contain its own embedding plus context from previous tokens, and ready to pass into decoder cross attention. Now, decoder cross attention, what we say by decoder cross attention, actually, we will take the Q that we have it from decoder, and we will take the K and V from the encoder. So if I just take you back, so that's what means by decoder cross attention. So it means encoder decoder attention. So it's a cross from both. So we take this one is the output Q from the decoder, and from the encoder, which we had it in previous classes, we'll take for example, I'll show you. So we'll take K and V here, uh, K and V from encoder, and they will be getting into, see that's K and V, they will come with the Q from here. So Q from encoder, Q from decoder, Q from decoder, and K and V from encoder. So just to do it one more time, just to show you a better representation. So, okay, so from the encoder, get the pen. From the encoder, we take this line, and that is here and here. So it'll be K and V from the encoder, and from the decoder, that is the Q that we have. And this Q can go there, and Q can go to multi-head attention. So this multi-head attention, it is cross attention, which is encoder decoder cross attention, which is encoder decoder attention. So stay tuned, and we will explain next class multi-head attention, which is cross attention. That's cross attention from the input from encoder, the refine input from the encoder, and uh, refine output Q from decoder. Stay tuned, and if you have any problem, please find the links there. Thank you very much, and stay tuned.